Greenhouse gas emissions are causing the stratosphere to shrink. The stratosphere has thinned by 400 meters since the 1980s and will thin by another kilometer by 2080, scientists have determined. Greenhouse gas emissions are responsible. These changes could impact satellite operations, GPS navigation systems, and radio communications. An international team of climate scientists has found evidence that human-produced greenhouse gases have caused the stratosphere to shrink. The findings, published in environmental research letters, demonstrate the profound impact humans are having on the planet. The stratosphere extends from about 20 kilometers to 60 kilometers above the Earth's surface. Below it lies the troposphere, a layer extending from the planet's surface to about 20 kilometers. The stratosphere, thanks to its ozone layer, plays a significant role in absorbing harmful ultraviolet radiation. However, as recent measurements have shown, this layer is shrinking. Until now, the loss of stratospheric thickness was largely attributed to ozone depletion due to the widespread use of chlorofluorocarbons, CFCs, over many decades. However, the gradual phase-out of CFC use has allowed the ozone layer to recover significantly over the past 20 years, alleviating concerns about permanent damage to the stratosphere. But new research reveals that the stratosphere continues to shrink even as CFC use has declined and the ozone layer has largely recovered, suggesting that another factor must be driving this disturbing trend. Previous studies have shown that the troposphere is thickening due to greenhouse gas emissions. This suggested that the stratosphere is shrinking due to pressure from below, but the new study is the first to demonstrate this. In a new study, scientists sought to learn more about the impact of greenhouse gas emissions on the stratosphere. They acquired satellite data dating back to the 1980s and added it to a computer model that also took into account chemical interactions in the atmosphere and the influence of the ozone layer. They also compared this data with climate models that accounted for increased carbon dioxide emissions during this period. These emissions cause the troposphere to heat up and expand, thus compressing the stratosphere from below. The models also showed that as carbon dioxide entered the stratosphere, it had a cooling effect. This temperature drop forced the gases in this atmospheric layer to contract, leading to even greater stratospheric depletion. Calculations showed that since the 1980s, the stratosphere has thinned by about 400 meters, which translates to about 1% of its thickness. Further model development showed that the stratosphere will continue to thin as long as greenhouse gases are emitted into the atmosphere. Scientists suggest that the stratosphere could shrink by as much as a kilometer over the next 60 years. The models also showed that changes in the ozone layer had little impact on the stratospheric thinning. According to the researchers, the continued shrinking of the stratosphere correlates well with steadily increasing greenhouse gas emissions over the past 40 years, suggesting that our emissions are indeed responsible for this change. We found that the stratosphere has been shrinking by more than 100 meters per decade since 1980. We also proved that this is caused by greenhouse gases, explained study author Juan Antonio Arnal from the University of Vigo in Spain. In the most likely climate change scenario, our planet's stratosphere could lose 4% of its vertical extent, or about 1.3 kilometers, by 2080, he added. Scientists note that it is still unclear what impact the shrinking stratosphere might have on the planet, but they point out that it could affect satellite trajectories and the way radio waves propagate, which could ultimately impact GPS navigation. Newly developed concrete could help purify the air. We'd all probably want the air around us to be as clean as possible. But how can we achieve this? Thanks to the work of Korean engineers, it will be possible to use concrete for this purpose. A new type of light-activated concrete they have developed can absorb pollutants from the air and transform them into harmless products. Air quality in cities is primarily shaped by road transport. Car exhaust pipes release hazardous nitrogen oxides and particulate matter into the atmosphere. But Korean scientists have found a solution that could help purify the air in cities. Surprisingly, it's concrete, or rather, a certain type of concrete. Air purifying concrete isn't a new invention. It was first introduced several years ago. However, what South Korean scientists have proposed is a special titanium dioxide coating that can significantly improve air quality. The description and results of the research were published in the KSCE Journal of Civil and Environmental Engineering Research. A team of engineers from the Korea Institute of Civil Engineering and Building Technology, KICT, set out to create a photocatalytic concrete whose ability to purify air pollutants relies on its outer coating. This layer, in turn, is made of titanium dioxide. Various application methods have already been tested. The first attempt involved adding a titanium dioxide solution to the already mixed cement. However, the end result was unsatisfactory, as it negatively impacted the cement's cohesion. The next attempt involved using pretreated titanium dioxide dust, which was then added to the cement, which had been mixed with it. This time, the resulting material had slightly lower porosity than the previous attempt, but this still weakened the mixture. The third time, the engineers decided to apply a layer of titanium dioxide directly to the concrete using a spray. This solution not only didn't negatively impact the concrete's porosity but actually strengthened it. Furthermore, it allowed the applied titanium dioxide to directly interact with airborne pollutants. The titanium dioxide layer mentioned above is activated by sunlight. At this point, it begins to produce reactive oxygen species, ROS. These ROS then react with pollutants present in the air, such as ammonia and nitrogen oxides emitted by cars. These compounds are broken down into chemical compounds that are no longer harmful to us. Korean engineers tested their improved concrete in practice. They placed it in a road tunnel, where artificial light was turned on to activate the surface layer. The improved concrete was then left in the tunnel for 24 hours. After this time, air pollution levels were measured and found to be 18% lower than before the test. And remember, for example, in tunnels where cars pass, the air is up to 1,000 times more polluted than the air outside the tunnel due to exhaust fumes. The new type of concrete converted nitrogen oxides into a form of salt that, under natural conditions, would simply be washed away by rain. Of course, in the tunnel itself, it had to be removed manually. The Koreans' next step will be to attempt to increase the effectiveness of their newly developed layer. They hope to successfully introduce it to the market. If such a device were to become widely available, it could significantly improve air quality in many cities currently struggling with this problem. Fast detection of neutrinos from the Milky Way. A new look at the galaxy. Scientists from the IceCube collaboration have presented evidence for the emission of high-energy neutrinos, elusive particles that weakly interact with matter from within our galaxy. Data from the IceCube Neutrino Observatory, a particle detector located deep in the Antarctic ice, allowed these particles to create an image of the Milky Way. The IceCube collaboration is an international project bringing together over 350 scientists from around the world. Its mission is to study neutrinos using the IceCube Neutrino Observatory, a detector located deep beneath the Antarctic ice sheet. In their latest publication, the scientists presented evidence for the emission of high-energy neutrinos from the Milky Way. This data allowed them to construct an image of our galaxy using neutrinos. The results and description of the research were published in the journal Science. Neutrinos, along with photons, are the most abundant particles in the universe. However, a little is known about them because they are the most elusive of the currently known elementary particles. Furthermore, they interact very weakly with matter. So weakly, in fact, that they are often referred to as ghost particles. Neutrinos have an incredible ability to penetrate. Even a planet like Earth poses almost no obstacle to them. Scientists estimate that 65 billion neutrinos pass through 1 square centimeter of our planet's surface facing the Sun every second. These particles, in enormous abundance, penetrate our bodies every second, and we are usually unaware of it. Neutrinos are electrically neutral and therefore not deflected by cosmic magnetic fields as they travel through space, meaning that the direction from which they arrive indicates their actual source. The first speculations about neutrinos' existence arose in the 1930s, but their first experimental observation occurred almost a quarter of a century later. Research has revealed that at least 3 types of these particles exist: electron, muon, and tau neutrinos, and each has its counterpart in the world of antimatter, meaning each has its own antiparticle. These particles have no electrical charge and are created in nuclear reactions within stars, as well as in reactors on Earth. Relatively recently, it was discovered that these particles oscillate, that is, constantly transforming from one type to another. This phenomenon means that the observed neutrinos must have some, albeit very small, mass. Without knowing the mass of neutrinos, our understanding of the universe will remain incomplete. In research last year, scientists were able to establish an upper limit for the neutrinos' mass. By measuring the energy distribution of electrons released during tritium beta decay, physicists determined that a neutrino has a mass no greater than 0.8 electron volts. Studying high-energy neutrinos will not only help us better understand the turbulent events constantly occurring at the interface between Earth's atmosphere and space, but will also shed more light on the nature of the interactions of these difficult-to-detect particles. But how can we study these elusive particles? Demonstrating their presence is incredibly complicated, as most of these ghost particles penetrate the entire Earth. Only in very rare cases do neutrinos interact with their surroundings. They sometimes interact with water molecules, creating byproducts called muons, which can be observed as flashes of light within the detector's sensors. Based on the patterns these flashes create, scientists can reconstruct the energy and sometimes even the source of the neutrinos. However, to observe them, scientists needed a truly quiet location. The IceCube detector, located near the South Pole, met these requirements. This detector, operated by 49 scientific institutions from 14 countries, uses thousands of photomultipliers to monitor a cubic kilometer of ice deep beneath the surface. Photomultipliers detect subtle flashes of light initiated by the interaction of ice-forming particles with neutrinos. The gigantic detector consists of over 5,000 such optical sensors suspended on 86 strings that hang from holes drilled into the Antarctic ice. The holes can be up to 2.5 kilometers deep. IceCube detected high-energy neutrinos, whose energies are millions to billions of times higher than those produced by stellar fusion reactions. The intriguing thing is that, unlike light of any wavelength, for neutrinos, the universe outshines nearby sources in our own galaxy, says Francis Halzen of the University of Wisconsin-Madison and IceCube's principal investigator. As is often the case, major breakthroughs in science are made possible by technological advances. The capabilities provided by the highly sensitive IceCube detector, combined with new data analysis tools, have given us a completely new view of our galaxy, one that had previously only been hinted at. As these capabilities continue to be refined, we can expect this image to emerge at increasingly higher resolution, potentially revealing hidden features of our galaxy that humanity has never seen before, notes Denise Caldwell of the National Science Foundation, NSF. Observations of high-energy neutrinos to date have shown that most of them originate from extragalactic sources, such as active galaxies far beyond our own. Gamma-ray observations, in turn, have revealed bright emissions from the plane of the Milky Way. Gamma rays and neutrinos are thought to be produced by the same astrophysical processes, so the Milky Way has long been expected to be the source of neutrino emission. However, previous searches for a neutrino signal from our galaxy have not yielded conclusive evidence. These searches have focused on the southern sky, where most neutrino emission is expected to originate from the galactic plane near the center of the Milky Way. A breakthrough came with the implementation of machine learning methods developed by researchers from the IceCube collaboration and the Technical University of Dortmund. Applying new techniques to data recorded over the past 10 years by the IceCube detector, scientists have found the first statistically robust evidence of neutrino emission from the inner regions of the Milky Way. According to the scientists, this detection proves that the Milky Way is a source of high-energy neutrinos, and their observed excess is consistent with the distribution and expected interactions of cosmic rays in the galaxy. The improved methods allowed us to identify more than an order of magnitude more neutrino events with better angular reconstruction, resulting in an analysis that is 3 times more sensitive than previous searches, says Marco Hanfeld from the University of Dortmund, also involved in the IceCube work. The dataset used in this study included 60,000 neutrinos, about 30 times more events than the selection used in previous analyses. These neutrinos were compared with previously published maps showing locations in the sky where the galaxy should glow with neutrinos. This created a fascinating picture of neutrino sources throughout our galaxy. The image shows that neutrinos are predominantly produced in regions with previously detected gamma-ray sources, confirming earlier suspicions that many neutrinos are produced as byproducts of cosmic rays striking interstellar dust and gas. Observing our own galaxy for the first time using particles instead of light is a huge step, says Naoko Kurahashi-Nielsen, a professor of physics at Drexel University. With the development of neutrino astronomy, we will have a new lens through which to observe the universe, he adds. Seeing our galaxy with neutrinos is something we've dreamed of, but for many years it seemed out of reach for our project, says Chad Finley of Stockholm University and one of the IceCube team members. What makes this result possible today is the revolution in machine learning, which allows us to explore our data much deeper than